Ladies and gentlemen, dear colleagues, I welcome you to this series of new colloquia on portable XRF, X-ray fluorescence, in art, archaeology, geoarchaeology, initiated by the Global Portable XRF Network and endorsed and supported by our Academy, the European Academy of Science and Art. This is a follow-up on a specialized section of the successful colloquia Arts Meets Science of the Academy for the last 4 years, thanks to these moments that there was frequent communication between the participants, which led to valuable collaborations, publications, symposia, etc. And also a follow-up of the expert group STEM in Arts and Culture of the Academy, of the European Academy. We thank Michaela and myself, Doris Klida, and Liritzis, who is not at the moment here, for technical support. And it is a great honor to have with us the president of the Academy, Professor Klaus Meinger, whom I would like to invite to greet our meeting and the new colloquia. Klaus.
Yeah, thank you very much, Ioannis, as president of this Academy. It's my pleasure to open this new specialized section of the successful lecture series Arts Meets Science. As you remember, Arts Meets Science was introduced at the very beginning of this presidency to emphasize the profile of our Academy, namely to combine arts and sciences. This series was initially moderated by the Dean of the Art classes, Violeta Dinescu, and the Dean of the Science classes, Ioannis Liritzis, currently followed by the Dean of the Medicine class, Dusan Shuput. Another project of this presidency was an interdisciplinary thematic network right from the beginning, in which major challenges facing Europe were addressed in position papers, so-called white papers, of the Academy, coordinated by the deans of the Academy across all boundaries of classes and disciplines. And the thematic network included, first, digitalization and AI, secondly, the energy problem with environmental and climate issues, and a third focus dedicated to interdisciplinary training and education for Europe. The recent breakthroughs in AI, China, US, and so on, and in this week, the summit AI in Paris, and its deep impact on the financial, economical, societal world demonstrate how we in the European Academy, with our white papers, had the finger on the pulse of time in which these challenges were discussed. Now, by the way, this discussion will be continued in our workshop in Salzburg on March 6th. That is the Thursday before the election and the festive assembly. And to all of you, cordial invitation for this event. Now, all that gave rise to the STEMAC project. As you probably know, STEM is an abbreviation for S, science, T, technology, E, engineering, and M, mathematics, and it is used internationally to emphasize education in the technical, mathematical, and scientific subjects. In line with the profile of the European Academy and its classes, STEM should be linked to the arts and cultural sciences, as in the abbreviation A for arts and C for culture. This is how STEMAC came about, and we have already had numerous individual events about it in the Academy. I'm delighted that Ioannis Liritzis and Michaela Schauer are now starting a collaborative event between the technical and scientific subjects and the arts and cultural studies. This evening, modern archaeology today works with highly specialized technical measuring methods and computer modeling. Applying them to the arts and cultural studies is therefore a prime example of STEMAC. As example, this evening we will hear two presentations on portable X-ray fluorescence. Tonight's topic is not only interdisciplinary, but also international. The speakers of the first lecture are from Portugal, and the speaker of the second lecture is from Australia, and the coordinator from Greece, and so on and so on. So you will experience the European Academy at its best this evening, namely interdisciplinarily and internationally. I hope you enjoy our event, and I wish you an exciting discussion. Thank you.
Thank you, Klaus. Thank you very much. Always present in our colloquia. Thank you. I would like to introduce the first speaker, and then Michaela Schauer, Dr. Michaela Schauer, will introduce the second. So the first speaker is Sofia Soares, if I could say Sofia Maria Mesquita Soares, okay, graduated in geology from the Faculty of Sciences of the University of Porto, Portugal, with a master in georesources, geotechnics area from Instituto Superior Técnico, and a PhD in geological engineering from the Faculty of Sciences and Technology of Universitat de Lisboa in 2012. She is currently a geologist at the National Energy and Geology Laboratory, being responsible for the survey, archive, lithoteca, and Alfreside. She has participated in many research projects and of geoarchaeological interest, and taught as assistant professor in the Beja Polytechnical Institute, Superior School of Technology and Management, subjects in geophysics and geomorphology and soil science. She has published more than 30 articles in international journals and participated in EU projects of training. I would like now to give the podium to Sofia, and next time will be the introduction by Michaela to the next speaker. Sofia, the podium is yours.
Thank you very much. Thank you very much for the invitation. I will share my presentation now. Okay. You all see it?
Yes.
Okay. So we are very glad to participate in this group with our experience and with some practical cases that we do and that we have started in here in our institution. This is not passing. Okay. So this is the contents that we'll talk today. First, we'll start for an introduction to the team and to the place where I work. And then we'll start by telling you why and how we use pXRF in geological materials here. And then some elements about the equipment and the principles of operation, the methodology that we use. Then we'll have some case studies and some further conclusions. So starting by the team, because my two colleagues are also here, the team is also multidisciplinary. So we have Teresa Pena. Teresa is our expert in chemistry. She is also a researcher here in the National Laboratory of Energy and Geology. And Patrícia is our expert in geoarchaeology, and she is a researcher at the University of Lisbon. We all, the three of us, we do some work in geology and geoarchaeology, and we have several projects together. So we are the task force here for the portable XRF. My institution, the Portuguese National Laboratory of Energy and Geology, has the heritage of our geological survey, the Portuguese Geological Survey. Now we have two main areas, the energy and geology. Me and Teresa, we belong to geology. I belong to the unit of geology, and Teresa belongs to the unit of mineral resources. Our institution, we have facilities in Portugal, in the different places of Portugal. We have facilities in Porto, in the north. Here in Lisbon, we have facilities dedicated to geology, to energy, and we also have our geological museum. And we have also facilities in the south, in a small village called Aljustel. And why do we have facilities here? Because it's not a main town. We have facilities here because here we have two mines working, and we have here important mineral resources, as it is the Iberian Pirate Belt. So LNEG mainly develops work and in the geology on geological mapping, on searching for mineral resources, and we also have lithotech, where indeed we have 3 lithotechs, one in each of these facilities that I've talked about, and we also give some support to archaeological work, especially because in our geological museum we have a very important collection of prehistoric archaeology and also paleontological and stratigraphic collections. So this is the main work that we do, and we use mainly our equipment to do works in these fields. So most of the times we can collect rocks and minerals or other sediment samples, and we will test them. These tests can be done in the field, in situ, or we can collect the samples and bring them to the lab and do the tests in the bench. Here you can also see that, you can also see that as we have core library, we have lots of cores, and most of the times we also need to do some tests directly in these cores. The cores, the sampling of the cores, sometimes it's not possible because we don't want to destroy the little bit of the core, and so we use the equipment directly in these cores. Also, in fossils and archaeological samples, it's very difficult, and it's not possible to obtain samples or to collect a little bit of the samples. So we use the equipment directly in our samples. Sorry. Okay. So our equipment, we have 2 equipments like the one that I'm showing you. 2 equipments from Hitachi XMET 8000 Expert Geo. The characteristics of the equipment are here because it's very important that we know what kind of equipment do we have. Here we have the possibility to do tests like mining light elements, fundamental parameters, or there's another option for rare earth elements that I will talk a little bit later. So here it's our equipment. We have the bench that you see here, and it's also possible through this little support to, in small samples, not to use the bench, but to use just a cap. The bench is easier to work with because we connect it directly to the computer and the results go directly to the computer. Also important in our work, it's knowing exactly the limits of detection that we have, and also know the elements that we are able to read. For instance, one of the limitations of our equipment is that among the light elements, it doesn't read lithium or sodium. So for us, it's a limitation that we have to take in account. Just put it there. So how do we do our tests? There is an internal protocol that we use and that we always do each time we have work and we have samples to analyze. First, we have to calibrate the equipment. So the first thing we do is use standards that we have, standards that were provided with equipment or our own international standards, and we will test these standards to see if the equipment has no problems on readings. Then we also do sample preparation. For instance, if there is a sample of a fossil, we clean the fossil, we clean the sample, and then we put it on the bench and we analyze it. Normally, our measurements are required during 60 seconds, 16 seconds for mining light elements, or 180 seconds if we are using the rare earth method. Normally, we do 2 or 3 points on each sample. If the sample is very, very small, we only do 2 points, but usually we try to do 3 points on each sample, and we do multiple tests for have the average at the end and improve the accuracy of the equipment and results. Whenever it's possible, we prefer to have a reading sample because the sample will be more homogeneous and it will be easier to get to do the tests and to have better results. And you see here the kind of sample the cup that we use, 32 millimeters diameter cup with the pXRF film here. As I was telling, fossils and archaeological materials usually are not tested as homogeneous samples, so we have to be very careful and do as many points as we can to have better results. We also have to take environmental conditions into consideration, especially if we do this sampling in the field or if we go directly with equipment in the field. But even in laboratory, we must ensure, for instance, that the samples are dry, there is no water, and that and all the environmental conditions are good. And also, of course, prioritize safety measures. Here are some results and a resume of what I was telling you. For instance, in this case, you can see that with the method for rare earth elements, we did 180 seconds, and for the mining one, we did only 60 seconds. This is how our equipment looks like, what we can choose, changing the name, the settings, and choosing the method. And we also have the possibility to have results in elements or in oxides. And we can also have the results in with percentages or in parts per million. So the case studies that I will present you today, there are 3 case studies directly connected with geology or with mineral resources. The first one is about calcretization and trying to find the calcium carbonated source. I don't know if all of you know what calcrates are, but usually in places with water content or connections with water and semi-arid and arid environments, we can develop process of calcretization that are due to the precipitation and accumulation of calcium carbonate in soil or even in the rock if the rock is fractured and the rock matrix. So, but the problem we had, it was in one of our lithological zones, the Osamurenda zone, and we have lots of different kinds of rocks. We have igneous rocks, and we have sediments, and we have metavolcanic and metasedimentary rocks, and we saw that this calcretization was affecting all these kinds of rocks. So we were trying to see if we could found where all this calcium carbonate came from, especially in granite and in the miocenic sediments. These miocenic sediments, as you can see here, are many times these big blocks of conglomerates. And here you can see the profile where you can see the granite here. This is a hammer, so you can have a scale here. And you have all the top and some fractures inside the granite that have calcrete. So one of the other objective that led us to do this study was also to compare the analysis taken in the field with the analysis that we could do in the bench tests. So it was a field acquisition and bench tests comparison. Showing you where is the, sorry, showing you where it is, the project. We have here the geological map of Portugal, and we are here. So this is Lisbon. This is really near the border with Spain, and this is a new railway project that wants to put this railway here to connect the ports of Sines, mostly here in the shore, with the border with Spain. So we went to see the last part of this corridor, and we did some tests in these local slopes and some quarries. Here are the places where did sampling. The blue one is the granite, and the yellow one is the sediments, the conglomerate. And here you have an ideal profile of calcrete, showing you that we had lots of different kinds of calcretization, and especially in the sediments in the conglomerate. And here in the granite, you can see that it was very, very fractured here, and all the fractures were fulfilled with calcrete. So we did 17 points of sampling among excavation slopes, including a quarry and a road slope. And in 6 of these locales, we did also vertical profile testing. So we did the vertical profile, we did directly measures with the equipment, and then we collected the samples, brought them to the lab, and did testing again in the bench. For granite, we can see here the results. We have granites with no weathering, with no calcrete, that have a very similar composition with the bibliographic composition that we had, and then calcrete on the granite, so the part that was already altered, we have very, very different values. So we see here that there is an increase of iron, of manganese, of calcium, very, very high values of calcium, and that the silica is very low, where we have calcrete. So we were trying to analyze these profiles and compare them with the profiles with the conglomerates, but the conglomerates are very different from granites and very heterogeneous. So you can see here that inside the conglomerate you have one nodule here, a very big one, that, sorry, that inside has lots of carbonates too. So this suggested us that at least 2 episodes of calcretization were here, so it wouldn't be so easy to make the correlation with this carbonatation as it was in granite. So conglomerate, as it is this sedimentary rock with lots of rock fragments, it's very heterogeneous, so it was much more difficult to do tests and to have reliable results than in granite. But the other objective, that it was compare the results between the bench tests and the tests done in situ. So you see here, we'll start our 0 at the bottom, and then we'll go to the top, to the part that was with the calcretization, and the results for the same point with the field results and the samples brought to do in the bench are quite similar, telling us that the results that we had from the field were reliable results. Sorry. The second case study, it was an ammonite that we found in Mesozoic, from Mesozoic deposits that was in the Pliocene deposits. So ammonites belong to Mesozoic, and here we had an ammonite in the middle of a Pliocene deposit in an old sand pit. This made us, first, it was not very common, and this made us wonder if the composition of this ammonite was similar to the composition of the other deposits that were surrounding it. So we took the ammonite and we took some nodules from the same unit. The location is here, it's a Tubal, it's near Lisbon, and the deposits that we are talking about are these ones, the yellow ones here, and the sand pit is here. And you have some photographs here. So this is the unit where we found the ammonite, and this is a nodule that was inside the same unit. So the idea was to compare and to understand what happened to that ammonite till she came here to these deposits where it was not supposed to be, because ammonites were already extinct when these deposits were formed. And we discussed it, and we knew that it was originally came from the Lusitanian Basin, and it came along with the deposits of the Tagus River, and it came to here, to these deposits, and we compared the composition with the tests, and we saw that the ammonite composition was different from the nodules that were in the same unit. The nodules, as you can see, are kaolinite ones, so they are mostly clay ones, and the ammonite revealed to be gypsum precipitation. So what we think that occurred was that all the carbonate and that the calcium carbonate that was in the ammonite in the beginning, it was dissolved by the acid sulfate rich waters and was fulfilled with the gypsum precipitation. So this simply test just made us understand that there are two kinds of elements here, very different, the kaolinite nodules, and maybe there are some other cobbles and pebbles with other origins, and we now want to continue these tests and continue to collect more cobbles and pebbles from this unit and to test several of them to have better results and to get to better conclusions. The last case study is a case study from work that Teresa was done, and it's also a paper publication. And the main of this work, the main purpose of this work was studying mining waste and trying to see if among these mining wastes we could find some critical and strategical raw materials, and to see if they are there and the amounts where they are there. So for this, they collected several samples along various mines, old mines, among the south, all of this in the south of Portugal. They collected these samples in many different types of mine wastes and deposit types too. And they brought the samples to the lab, they prepared the samples, and they tested it in the benchtop too. And in this work, they also did something important for us to have reliable results. They did something like picking up the samples, testing it with a portable pXRF equipment, testing it with laboratory equipment, and sending the same samples to activation laboratories at Canada. So at the end, we have results that we can compare, and as you can see here, we can see that the major elements have very good correlations between all the tests, and the difference that we have here in some points, in some samples, allow us to see what elements we have to be careful when we use our portable equipment. So you can see that all the elements that we have here, for instance, aluminium, copper, and iron, these elements gave us very good results, and some elements, especially the elements that were read by the red earth elements method, gave us some problems with the lowest reliability measurements. Also, these differences may be related to the difficulty of getting good samples for do the analytical tests. And here we can see a correlation between the content of elements found in copper and manganese waste in mines and evidence of these same elements in the Earth's crust. So we can see that in some of these wastes we have very interesting amounts of these elements that probably we can take a look at them and even try to think if it is possible to reuse these wastes and see if we can get these elements too. Some of these elements that you see here are very important elements as critical raw materials and as strategic raw materials, like, for instance, copper, that is one of the newest raw materials, strategic raw materials now. And here you have some of these critical and strategic raw materials for sample distribution. And we can see that some of these elements, for instance, like copper, they are present in many minerals like pearlesite, rhodochrosite, and other minerals. So for future directions and some conclusions, we use our equipment most of the times like a guide for decision making in geology, for mapping, for knowing which rock it is, for selection of samples to go to the lab, and for the first approach for mineral resources. And we think that the equipment proved to be a reliable and a very low cost effective tool, and we can only send to the lab the samples that we really have important samples, or samples that we have doubts, because for the first analysis our equipment gives us reliable results. But of course that we must be aware of the limitations, and these limitations go from the limits of detection. In our case, for instance, we don't have lectures for sodium, the number of analyses that we must do, the number of samples, the quality of the samples and the heterogeneity of the samples, and environmental conditions. And considering that there may be other sources of error, and that we must look at the results over the critical view. And of course, use calibration standards to make sure that what we are reading is exactly what it should be there. For the future, we have a new project that Patrícia is the leader, and it's called MoBlades project. You can see here, if you have interest, you can see more details about this project. And this is a project that we will also use our equipment to relate raw materials, especially for silica materials, to the use of blades. This will be the next challenge that we'll be facing with our equipment and other tests that we will also do. So the references of all the 3 case studies that I've showed here, and I hope I didn't took too much time. Thank you very much.
Thank you. Thank you very much, Sofia. It was very interesting, your talk, and the questions it will be at the end, I suppose. Tonight I noticed also is with us the Dean of Class 3 of the Academy, famous pianist and musician, composing music with mathematics too, Violeta Dinescu. I welcome her. And now I would like to pass on to Michaela, the next part of our session, but I would like here first to say that Michaela is the heart of the core of the global pXRF. Dr. Schauer is a senior scientist at the Vienna Institute for Archaeological Sciences and a member of the research network Human Evolution and Archaeological Sciences, specializing in chemical analysis using pXRF, portable XRF. She's especially interested in everything related to pottery, sediments, implications of studying these materials for past societies, and she's a prehistorian and Near Eastern archaeologist by training, specialized in the chemical analysis of archaeological geological materials using the portable X-ray fluorescence. Recently, she has completed her PhD at the Ludwig Maximilian Universitat in Munich. So, Michaela, you can follow up now.
Thank you, Ioannis. That was very, very sweet. I didn't expect that. But it's not about me now, it's about Michelle, and I feel very honored to introduce her. She's an archaeologist and a postdoctoral research fellow at the University of Melbourne in Australia. She's very brave to be with us at that time, because for her it's very early in the morning. So thank you for that. She has her own research project connecting Pacifica communities to the collections made by James Lyle Young. She studied at the universities of Sydney and the Australian National University, where she finished her PhD in 2021. She also completed a graduate diploma in environmental law at the University of Sydney in 2023. She lectured at the universities of Sydney and still does at the University of Melbourne. And she's focused and very interested in the development and application of non-destructive pXRF geochemical analysis to identify and characterize the origins of archaeological stone tools and to explore the exchange systems. She has a variety of publications that are going into that direction: standardization, how to apply the method in the field, and how to study rocks and stones. I found it very impressive that she also has an article in the Handbook of Archaeological Science, Lithic Exploitation and Useware Analysis. But she's not only writing and lecturing and doing all those other things, getting her own projects and getting money. No, she's also highly engaged in initiatives connecting the pXRF community and also working towards standardization of the method. So she leads the pilot research project, an Australasian pXRF archaeological researchers collective to standardize pXRF use for First Nation communities conducting archaeological research. But she's also, together with Ioannis and I, part of the core team of the Global pXRF Network, what we just started in September. So every one of you who isn't part of it, send me a message so we can get you signed up for the email list. So that's about Michelle. Michelle, I would ask you to start and tell us something about pXRF and stones.
Okay, I'll just, is that sharing the screen there for everyone?
It does, very nicely.
Yes, so yes, I am joining you this morning for me at 4 a.m. From the unceded lands of the Wurundjeri Woi-wurrung people, and I'd like to pay my respects to their elders, past and present. And apologies, I know this is being recorded, but it might be quite funny to watch back later how awake I am or not. So to begin, I'd like to think about how and why geochemistry is so important to archaeological studies. And that is, of course, for the people we're trying to understand in the past. So the provenance studies of raw materials used to create the artifacts that circulated in prehistoric exchange systems, of course, are fundamental to archaeological exchange models. And exchange studies in archaeology have aimed to understand the past human behaviours by studying the patterns of artifact, resource, distribution and social models that we use to reconstruct the processes involving, prestige, status, social networks and hierarchies. And of course, a requirement of many geochemical provenance techniques is the need to destroy or destructively analyse some of these artifacts. However, these destructive approaches are not appreciated as much by First Nations communities wishing to analyse the objects that belong to their ancestors. Of course, so thinking about how to create studies where we use pXRF to geochemically provenance materials is an important way of engaging with First Nations communities who wish to engage with archaeological studies and conduct their own research. So importantly, less attention has been given to finding geochemical methods that are appropriate to this suite of elements that are detected reliably by pXRF analyses, meaning that the technique can be underutilised in geological provenance studies. One of the greatest challenges in provenance work is finding structure and significance in the geochemical data based on these geological principles. So importantly, the statistical significance, so finding the groups or clusters that we see on bivariate scatter plots, is not always the same as correlating the artifacts between their sources based on petrogenic processes. So understanding the common material types or rock types that occur at multiple sources is the first step in source discrimination. So, I'll just, for this presentation, I'd like to look at the trace elements that we can focus on and introduce the Pierce Winchester-Floyd diagram as a proxy to the total alkali silica diagram, which has been used quite extensively in the Pacific in archaeological studies. That's where I conducted my PhD and kind of stumbled across this diagram when I was looking at the history of archaeology. I thought, hang on a second, there's also a history to geology. Let's have a look at some of the ways we decided to come up with these rock classifications in the first place. Now, of course, the TAS chemical classification diagram is a bivariate scatter plot of sodium oxide plus potassium oxide plotted against silica oxide. And this is used for determining volcanic rock types. And this diagram, as I mentioned, has been widely used in archaeological basalt studies in the Pacific. Now, these elements can be detected with EDXRF analyses, but this sort of is limited. The benchtop EDXRF instruments can be used, but you have to be able to fit the artifact inside the chamber. And other destructive analyses, such as WDXRF or ICP-MS, are much better at giving you accurate concentrations of these elements. So pXRF doesn't really give you sodium. You can sort of see potassium, and silica also, there can be some issues in finding that as well. As well, on this diagram, you also have the division between alkaline and subalkaline basalts, which, as you can see here, there's been several lines drawn on the diagram to try and, decipher exactly where this is. This is kind of a limitation of this diagram. It kind of relies on a 50-50 probability of the basalt being either alkali or subalkali. And there's a silica under saturation plane that occurs across the middle of this diagram, forming quite an overlap in this region. So using this to try and determine alkalinity has been debated over the years by geologists. So, of course, for pXRF, though, the main limiting factor for this diagram is the requirement for destructive analyses, which we can avoid if we want to use pXRF. Instead, the Pierce WF diagram, which I picture here, was devised originally by Winchester and Floyd in 1977, and it plots the zirconium against titanium dioxide, against niobium and yttrium. And this was developed prior to the TAS diagram being developed in 1986 and accepted as the official way of classifying volcanic rock types. Subsequently, Pierce in 1996 revised this diagram and importantly set the division between alkaline and subalkaline basalts at 0.67 on the x-axis here, so the niobium and yttrium ratio, which does give us an indication of alkalinity. and also the alkaline and ultra-alkaline here at 3.9. So here we can see the different material types, rock types of basalts being plotted here. Now, the Pierce WF diagram is similar to the TAS diagram and can be used as a proxy, but it's important to understand that the materials don't directly correspond with one another, but the diagram does distinguish between basic, intermediate, and evolved rocks and alkalinity. So it does provide a systematic way of grouping rock types non-destructively using pXRF data. So it's a crucial first step in getting your material types together before you run multivariate statistics such as discriminant function analyses or classification trees. So just to give you a visualization, when you sort of move those types across, you have that flip of the alkalinity, which is measured by sodium and potassium on the TAS diagram, flip down to the niobium and yttrium axes there. So I'll take you to the Pacific for my case studies, which were all part of my PhD research. So it's quite convenient that there is this lovely andesite line that exists in the Pacific. So we have generally more subalkaline basalts in the west and more alkaline in the east. So when we're looking at the island groups of Fiji, Tonga, and Samoa, for example, if you have adzes that were traded across these and between these islands across this border, you can start to determine which artifacts have come from which island group. We also have hotspot geology, which means you have a volcano beneath the tectonic plate producing these islands over time in kind of a production line, if you will, that produces the different archipelago chains. So you have different archipelagos all coming from the same volcano deep beneath the sea over time. And these are all ocean island basalts. So it's quite nice to be able to work with this material. It's kind of ideal, second probably only to obsidian. So in the past, studies have relied on EDXRF and pXRF analyses, but they've gone and used destructive analyses to plot the results on the TAS diagram to really confirm their ideas about the movement of these artifacts based on their alkalinity. So for instance, if we head over to Fiji, Samoa, and Tonga, as I was just talking about, this study by Clark and colleagues in 2013, they looked, they used pXRF, but they also used the SEM EDAX and the lighter XRF on 68 samples to be able to plot these on the TAS diagram. We have the alkaline basalts up here and the subalkaline down here, and they were able to separate out the Fijian and Tongan artifacts from the Samoan artifacts. I went to their supplementary materials and got all their pXRF data and plotted them on the Pierce WF diagram. They used a Teresa 3B, which is one of the older generation XRFs. And I would love to be able to recalibrate this because I think you could get these a little bit more refined. But nonetheless, even with the older pXRF data, we were able to separate the Samoan samples here, which are the alkaline ones, so these ones up here, from the subalkaline samples. So that increases your sample size from 68 up to 216 that can be plotted here. Likewise, in Khan and colleagues' study from Tahiti and Moorea, you'll see here they used WD-XRF for about 67 samples that could be classified on the TAS diagram, both alkaline basalts, but two separate groups clearly emerge. Using the pXRF diagram and all the EDXRF data they used on 198 samples, were able to get the same groupings on the pXRF diagram. So again, this really increases the volume of samples that can be classified non-destructively. Heading over to Hawaii now. Here we had 9 WD-XRF samples that were used in a paper that plotted again on the TAS diagram. When we use the pXRF diagram, we're able to include all 328 artifact samples, as well as plot the 1,452 studies that were conducted previously, including geological reference materials. So in terms of thinking about the geological reference materials, this is what I was aiming to do in my PhD, was to plot as much archaeological data to build up a reference collection of archaeological material. So this is all the previous studies mentioned here, plotted on this diagram. You can sort of see most favoured were the alkali basalts for making stone adzes. And then I increased that even more for my PhD and included data from the GeoRock database, which is maintained by Max Planck. And I was able to take out all the data available there. There it becomes a bit more complicated. You have all sorts of geological studies in this database. You'll notice here, for instance, the orange dots are from the Marquesas Islands, of which there were many studies conducted because the Marquesas were going to be the Bikini Atoll of the Pacific, and the nuclear testing was, you know, for a while they thought about destroying this archipelago, but in the end they ultimately chose the Bikini Atolls instead. But that's why there's so many geological studies available and geochemical information from the Marquesas group. So when I then plot the artifacts, so the adzes that I looked at in my PhD, on this graph, you'll see there's the clusters sort of neaten up a little bit. So these are the archaeological quarries that, you know, people selected for the best basalts. Then we sort of look at the pounders here. That becomes a bit more messy, and I'll talk about that a bit more in just a moment. Again, the previous archaeological studies, when you plot them out, you know, you get some nice groupings here between the Marquesas Islands, Society Islands, the Austral Cook Group, and Rapa Nui or Easter Island up here plots out quite separately. So looking at the pounders, which is a kind of understudied artifact class from the region. So the stone pounders, known as Kikatu Papoi, were and are still used on certain Polynesian islands to mash food, usually breadfruit, and they created a paste known as poi. Some were used to produce medicine and others were used to produce pigments. These were actually the second most frequently collected stone objects in Polynesia after adzes in the colonial period, and they're now numerous in global museum collections. Yet they've not received as much archaeological attention. So stone pounders provide a way of studying the colonial period and the impacts of colonialism on the production and circulation of traditional Polynesian objects. And they can be compared with adzes from earlier and more recent pre-contact and early colonial periods in the Pacific. So you can see here when you use a discriminant function analysis, you're actually able to separate the island groups out even further. So when I looked at this particular type of tiki-headed pounders that were in the museum collections, they all group with the Marquesas. And focusing in on the Marquesas, if we look at the all the geological data available in the GeoRock database, and we plot that on the pXRF diagram, we do see a division here at 1.2, which actually correlates between the northern islands here, so Nuku'hiva and Iao in particular, which are known to have adze quarries on them, are all in the green spots here. Whereas the southern islands have, a more subalkaline basalt. So they are all grouping together over here. Again, running this through with the artifacts through a discriminant function analysis, you'll see that Hiva-Oa and Tashuhana, what the actual locations where the two different sort of forms of the tiki-headed pounder could be sourced to. So you have the big goggly eye ones up here, all coming from Hiva-Oa, and the smaller eyed form all coming from Tauhata. So these objects were found in all different locations throughout the Marquesas. So they were moving around, but just locally within the group. And that seems to be the case for pounders across all the Pacific. And there is some suggestion from my results that people from neighbouring groups such as the Society Islands were coming over to get the Marquesan basalt to create their pounder forms, but these forms stayed within their local groups. And that's very much in contrast to the adzes. So adzes from the Marquesas, the best ones came from Iao, that was the finest basalt, and Nuku'hiva as well. So you had this sort of, we'll switch now to look at the adzes. They were travelling much further across the Pacific, and not in just one direction, but back and forth as well. And I did look to see if there was a map of Europe overlaid across the Pacific to give you an idea of scale, but no one's done that yet. So that's something I will work on. But of course, we're looking at, thousands of kilometres here. People were voyaging in canoes. My results, my PhD, that was nothing really new. We'd known that the EAR source had been favoured archaeologically for a long time. And as well, we had this centre in Samoa where people went to get the basalt from there and move outwards. So if we've got time, have I gone over time? Or I can go a little bit into the current research I'm doing in Australia now, where there's been a bit less recent research. So since the 60s, if we come across to Victoria, Melbourne is over here. There's a lot of basalt here, young basalt, but it's all vesicular and it's not really great for making stone tools. So that wasn't the material that was chosen. So working with Taungurung Land and Waters Council, they're working in museum collections to reconnect to their cultural heritage. They're interested in looking at the greenstone axes from their country, which is up here to the north. We have these greenstone belts, which run north-south, which are metamorphosed materials. and they've come into contact metamorphism with granites as well as hornfells. So big squished belts of basalt, essentially. And these our preliminary results, starting with the PSWF diagram, are very promising. There's great separation between these types. So just a little bit of a preview. Based on, again, these sort of geological principles that, you know, when you have a basalt smushed against a granite, you end up with something in the middle, an andesite, but the different chemical compositions do vary between the sources, and we are able to see great results with the pXRF data there, and the community is very happy to have a non-destructive technique to use and visit the collections with, and to be able to use in their own, you know, day-to-day cultural resource management work as well. So just as a summary, geochemical rock classifications for stone artifacts are, of course, a crucial first step in your provenance analyses. So you want to be comparing apples with apples, not apples and bananas. pXRF can be used for rock classifications to tell us about the landscape and the tectonic setting. pXRF data can be compared to existing geochemical and archaeological data sets from other techniques such as ICP-MS or other destructive analyses. And the pXRF data can be used with multivariate statistical analyses such as discriminant function analyses or classification tree. And of course, there's huge potential here for machine learning and artificial intelligence for stone artifact provenance based on these geological principles. So this, of course, has been proven with igneous rocks in the Pacific, specifically ocean island basalts. But of course, there's huge potential for metamorphosed rocks in the future. So thank you very much.
Michaela.
Thank you so much. Sorry, needed to unmute myself. Thank you, Michelle. So if I got it right, Ioannis, we would be now going to questions.
Yeah, question to the first speaker, yes. Any questions? Yes. Yes, Sofia. No, for this first speaker. For Sofia Soares, any questions?
I don't find the hands here. May I ask a question?
Yes, yes, please.
Yeah. As I mentioned in my introduction, I'm of course interested, because I'm not a geologist and a chemist. I'm especially interested in the application to the cultural studies. And what is so amazing, I think, is that through the history of the different cultures, it depends on certain materials. We know that. We speak about the age of iron and the age of bronze and so on. And perhaps our period nowadays with AI in later times will be called the time of rare earths, because the rare earths are so necessary for batteries and transistors and whatsoever. Now, my question is, what I learned in your studies is you analyzed certain materials, for example, volcanic rocks in the Pacific, and then you mentioned certain tribes or people who use these materials in their culture. The phase transitions in the cultural development, which I mentioned before, depends on the mixture of the found materials in the regions where the people live. So my question is, did you also consider these mixtures of materials to come about with new innovations for cultural shifts?
Yes, so I didn't really go into the interpretation or the cultural side of my results there. But yes, absolutely. My entire thesis actually was based on dispelling an old typological study that had been used across the Pacific and continued to be used, you know, just in reference. I don't think many archaeologists, Pacific archaeologists, think that the conclusions of the typology were really correct, especially because it was used as kind of a proxy for chronology and the different developments of, the types of adzes coming out from Southeast Asia. The very early studies made very clear, blatant assumptions that people were frozen in time and only brought the shapes that were developed in Southeast Asia out into the Pacific, and based a lot of their early migration studies on that idea. Like I said, we don't think that at all now, but and the pXRF studies show that back and forth movement of exactly the same objects that were used in those initial studies. So yes, there's a big emphasis on, saying people got to the Pacific and they made a lot of their own adaptations and innovations with the materials they found on the different islands, including the invention of those stone pounders in particular, which, of course, could have easily been wooden pounders in, earlier times. That was a very regional development there. So yes, absolutely. The use and innovative uses of the materials that, different cultural groups came across and then shared by staying in contact with one another across, thousands of kilometers. Yeah.
Thank you.
If nobody dares, I would have some questions for Sofia. But they might be a little bit geeky. I was wondering, you said that you compared your pXRF results with bibliography of values and that they matched quite well. I would be interested in the quite well part. How do you define that they match quite well? And how do you bring together values from a bibliography with the pXRF values? So what's your way of bringing them together?
Thank you for the question. The only time we compare results from bibliography was in the granite. So what we did was we didn't have any results from these granites, and we had these granites are ornamental stones. So they were tested and there are results published. So we compare those values with the values that we got for just, how can I say, just to see if the granite was not weathered. So the values that we have from bibliography are values that is from a non-weathered granite. And what we were trying to see was if there were any changes that could indicate that the granite that we were considering as not weathered was really not weathered granite, or there was some grade of weathering already. So that's why we did that comparison. But that was just punctual one. It was not the purpose of the study. That was just as we had those values, we just compared it because it was the only values that we had that we were sure that were get it to a non-weather granite.
And the bibliography values, were they taken with the same device?
No, of course not. That's why we when we did this study, all the results that we got from the same device. And that's why when we get the chance in any studies that we do, we pick some samples and we send it to the lab to do tests in other laboratories to compare and to see the kind of results that our portable equipment gives us.
Thank
As
you.
I say here, for this particular point that you are asking, what we did was we had results in the labs. Actually, the lab was from our institution because we did these tests many years ago for ornamental stones. And as we had those results for granites, we compare it just to see if the grade of weathering was what we were expecting. It was just comparison with the values that we were sure that were from a non-weathered granite.
Thank you.
Other question? Yes, Marius Ioan Piso.
Thank you, Professor Liritzis. First of all, I would like to thank both presenters for two excellent descriptions of this method, which is widely used in the last years. But first of all, for the capability to transmit the information at, let's say, a less specialist level. And this is important, and this is in the spirit of the academy, which is, among others, multidisciplinarity. And I noted the description of technology utilized for portable X-ray fluorescence spectrometers, then the utilization in extreme conditions in the oceans. And I just wanted to mention that that kind of technology is utilized on the cosmic ships. It's widely utilized in planetary exploration. So the first Mars rover, which was Viking, which landed on Mars in 1977, it carried an X-ray spectrometer. And the most developed rover, which is Perseverance, has at the end of one robotic arms, has such a device. And another miniature X-ray fluorescence spectrometer landed on the comet in the mission Rosetta. It was the first landing produced by humankind on a comet, and due to that kind of spectrometry, it was able to bring very valuable information. This was only my comment, and we should think of multidisciplinarity and this of high quality and advanced methods, which are bringing every minute, are bringing our knowledge to new advances. Thank you.
Thank you, Professor Piso. Yes, indeed, it's a very versatile device and has been used extensively and very good, very interestingly observation to the planetary, science with curiosity, perseverance. Yes. Any other questions? Yes, Kidan.
Yes, thank you. I'm pleased to attend this one. I'm sorry I was not able to put the video, but I will ask a question to the two presenters. Can you hear me?
Yes, we
Yes.
hear you.
Yes.
That's great. So to Sofia, in the case of the ammonite, you have identified gypsum based on the elevated level of calcium and sulfur. Couldn't that be something? Did you get some information from complementary technique? As you know, XRF gives you elemental composition. Did you do some complementary analysis to claim gypsum? It could be in different forms of hydration. It may not be in hemihydrate, for example. anhydrite or something else. And regarding Michelle, that's impressive presentation. I enjoyed it so much. And in the case of the rock materials you are analyzing, they look like homogeneous, and that's nice. But wasn't there differences in terms of patination? Because XRF is surface sensitive, and your result for titanium, zirconium, niobium, and yttrium could be affected by weathering products on the surface. How did you experience that? And the other one is morphology of the objects. How did you do the investigation to maximize the analysis? You need to go so close to the surface, and it may not be consistent depending on the geometry of the object. And the third question connected to that is the way you quantified it. Was it matched to the metrics? What kind of reference you used? Thank you.
Thank you very much for your question. Yes, you are right. It can be anhydrite, of course. The reason we think it isn't is because in this kind of deposits, it's not the first time that we identify gypsum. So it's very common in this kind of deposits that have gypsum. In this particular case, of course, I can't ensure that, okay, this is really gypsum and not anhydrite, because it was a very small sample, and it was the unique one. We didn't find any other ammonites. But as I mentioned, we will try to get more nodules, because we also think that in the middle of all that deposit, maybe some nodules can also be from gypsum. And that's why we are going to do new sampling. All the data and the knowledge that we have from this unit indicates that that's gypsum and not anhydrite. But there is a possibility, and yes, you are right, because the differences between those two, we can't tell by only these tests with the XRF. Yes, you are right. Thank you.
Yes, so
Thank
those were excellent questions. So in relation to titanium, zirconium, yttrium, and niobium, they were actually chosen by the geologists making the diagrams because they're considered to be immobile elements in basalts. So it was a very strong contender against the TAS diagram because those other elements are mobile. And other studies have been done in basalts, and it's fairly well agreed that those elements are immobile despite surface weathering, both as a basalt that exists on the surface for a long time that people had easy access to, so very long geochemical weathering, as well as weathering after use from being left out in kind of more human timescales. So those elements are very, very good and well detected by pXRF. So I didn't worry too much about the surface. You can clean the surface a little bit with hydrochloric acid to remove some of the carbonates. But even I looked at some objects that were recovered from the Pandora shipwreck off the coast of Australia in Queensland that were collected from the Society Islands, we mostly think. And those elements are even still okay. And those objects have been under the water for 200 years. So that's the elements. The surface morphology, yes, it's very tricky on the pounders. They were so concave. I had to use the old Teresa 3SD, which came with a kind of camera stand thing that you could move around. So there was a lot of trying to position the object with, you know, the conservators, foam and cushions, and get like some flat areas. To get around that, I did try and find 3 flat surfaces on the object to analyze in 3 different locations, and then I was able to average those results. For the calibration, I used 60 international standard reference materials, and those familiar with the old Tracer 3 SD, you have to work with the raw photon counts and quantify those, which was done in Excel using standard procedures. They're all in my PhD if you want to read the very nitty-gritty detail of it. Yeah.
That's great. Thank you. Thank you so much.
Oh, Klaus has?
Klaus Manzer, yes.
Yeah. I have a last question concerning my own field, you know, AI. And it was roughly mentioned, I think Michelle was in the end of her talk, mentioned it very shortly. I do not mean ChatGPT and all these stuff, because this kind of AI is too unspecific. It may be spectacular for the general user, but I mean in science now, here in geology and in your field. How far is machine learning applied and even specialized and even used by you and your colleagues? I think obviously pattern recognition is a typical ability of these algorithms, and in this huge amount of data that may be helpful. But my question is, how far is it already used, and how far are you and your colleagues trained to apply it in your field?
I would really like to be able to use it a lot more. Doing the multivariate statistics, I guess, manually, being able to enter that into a machine learning model or train an AI model to do what I currently use, you know, macros, or just sit there and click the button 100 times myself. I can see the application. I'm not currently using it at the moment. But yeah, I see the application, and once it's set up, it would be wonderful. And being able to go into those geological reference collections that I mentioned, to be able to kind of farm the appropriate information for archaeological studies would be wonderful as well. I don't know, do we have an AI machine learning special talk coming up in the series, in the colloquia? That could be.
No, we haven't. Not
no,
so
we-
far. So that's a very nice pitch. So if there's some suggestions about having that integrated as well in the lecture series, that would be amazing. I would also maybe hop on to Lee, because as far as I know, Lee is the one in our field who's doing the most work on AI learning and all those fancy things. So Lee, do you want to comment on that a bit?
Yeah. So I think, you know, with AI, I think one big shift that happens, and I've worked with a number of corporate clients as well as folks in academia. But the big jump is, instead of using XRF or another analytical to determine a quantity, such as rubidium 182 ppm, we're now going to inference. Now, with inference, there's lots of other things we can do. The craziest one I've seen is we're able to infer isotopic concentrations of lead using AI, but it's not determined the same way we're used to with XRF. So I think provided people are comfortable with that shift, then it becomes widely useful, because, and what I found is that rather than, you know, isolating to the peaks, the entire spectrum becomes useful. And my German colleagues informed me I mispronounced this, so I apologize, but the Bremsstrahlung radiation, the Compton scattering, the inelastic scattering, all that combines in extremely nonlinear complex ways to create new properties we can estimate. One of the surprises in my experience has been loss on ignition. Now, loss on ignition is where we take a sample, burn it at high temperatures, CO2 outgasses, water outgasses. We've destroyed and modified the sample, but its new weight conveys a property. Turns out XRF nails that every single time. But it's inference, right? We haven't actually outgassed all that material, but we can infer that from the scatter. So it raises a lot of interesting possibilities, but you first have to accept inference in place of determination with analytical data.
Yeah. Thank you.
Thank you, Lee. For Lee, it's late in the night, so we we have the late one and the early one with us, and both are awake. I'm impressed.
Yeah. So that's it.
Any more questions? Doesn't look like it. Do you want to close it, Ioannis?
Okay. Yes, it is a great pleasure to have the first session of our new colloquia. I think it was quite successful. I'm very pleased. And we look forward to see the participants and more next time, because this is a series of sessions. Thank you very much for your participation. Thank you very much, the President of the Academy, the Dean of Class 3, and all you distinguished members of the Academy, and dear colleagues. And have a nice the rest of the week. And I look forward to see you next. Michaela?
Thank you very much. If anybody has somebody to propose for the lecture series, just send them our way. We're very happy to hear new names, new ideas. And thank you to the speakers. Thank you to you all. Enjoy your day, evening, whatever you have. And see you next time.
Wherever you are, yeah.
Yes.
Indeed.
It's really
Very
global.
This evening, continents were connected,
Yes.
not only European countries. Yes, amazing.
Thank you all.
Okay.
Thank you.
Thank you. Thank you.
Thank you
Thank
very
you.
much.
Bye-bye.
Thank you
Goodbye.
very
Good
much.
night.
Bye.